Good day, statisticians. Today we're going to be taking a look at the idea of a population least squares regression line from the perspective of random variables and linear transformations of variables, right? So for instance, here I have a line. It's a line segment technically that goes from x equals 1 to x equals 10. And if you studied a little algebra 1, you could find the equation of that line and see that it is about y equals 2 plus 3/4 x. Now, in algebra 1, that would be just fine. But here in statistics, we can think of x and y as random variables. And here y hat, is simply a linear transformation of x, that you could perfectly predict what y is from x. So if x equals 8, you could plug in 8 times 3/4 plus 2 and get 8. And that's nice. But in statistics, when we're collecting data, very rarely do we have exact perfect predictions. Very rarely are we going to encounter situations where some variable y is a perfect linear transformation of x. Instead, there's errors. And so we can represent that by adding an extra random variable to our equation. Instead of y simply being a function of x, y is actually a function of x, but also this new random variable epsilon, where epsilon stands for our errors or our residuals. And the core idea for us is, regardless of whatever the distribution of x is, epsilon is going to be normally distributed. Our residuals away from our predictions are going to be normally distributed with a mean of 0. In other words, on average, our predictions are going to be correct. The residual on average of values should be 0, but there's always a standard deviation, a constant standard deviation for the amount that our actual observations will vary from what's predicted. And so let's just suppose, for the sake of argument, in this particular example, let's just let the standard deviation of the residuals equal 1. Then we could say epsilon is a normally distributed random variable with a mean of 0 and a standard deviation of 1. Now, what does this really do? Well, it takes basically what the line predicts, just plugging in some number for x, but then it changes reality, right? It accounts for the random variation that might exist in the world. For instance, if you're trying to predict how much a car is going to be worth depending on how many miles it has, you can probably get a nice linear relationship between those things. But there's all these other factors, that little error term. And the idea here is that error term will add or subtract value from the car. Similarly here. Here I could say if x equals 4, y is supposed to be 5. But let me pick a random number for epsilon. In the calculator, you can do rand norm 0, 1. That would give me a random value from the normal distribution with a mean of 0, standard deviation of 1, and it gives me 0.2309. So let's just say, okay, the line said y should be 5, but then my error term says, let's make it a little bit higher, 0.23 higher, with the residual 0.23. Similarly, say I plug in x equals 6. Well, according to my linear transformation, then y should be 6.5. But my error term says, here I just generated a new one. How about let's take that down 0.938, right? All right, that just got lowered. Let's go with the term that we already had. Remember, x was supposed to be, when x was 8, y was supposed to be 8. I just generated a new random residual, right? The residual of 2.146 approximately. And wow, that's a big residual. It lifted that point way higher than predictions. Let's add a couple other points. So here, when x is 10, our residual of negative 0.27, it could lower our observation a little bit. Similarly, when x is 2, let's get a new residual, 1.0666. That sounds dark. I'm going to move that point up a point. So the idea is here, I took 5 observations, 5 possible values that I could observe. And here I just arbitrarily picked values for x. But then that random variation that's represented by the epsilon term, which is a normal distribution with a mean of 0 and a standard deviation of 1, takes the actual, it represents what happens in reality, that the observations that we get are going to often be a little bit higher or a little bit lower. Now, based on those 5 points that I generated, I could come up with a least squares regression line. This would be a sample least squares regression line. I started with a population least squares regression line with a true slope of 3/4, but based on a sample of 5 points selected at random from this distribution, I get y hat equals 2.676 plus 0.7119x. Now, the thing that looks interesting to me in particular is the slope of that thing. The slope of 0.7119 is actually pretty close to 0.75 or 3/4, which was the population line. But this is a sample least squares regression line. Notice it shows that there is a strong positive linear relationship between these variables. It kind of looks like that to my I, and my R indicates that. R squared says 78.1% of the variation that I'm seeing in my Y values is explained by that linear relationship with X. And why isn't it 100%? Because my epsilon, my error term, right, my residuals, did not have a standard deviation of 0. If the standard deviation was 0, there would have been no variation from the line, and R squared would have been 1. But whenever the standard deviation of residuals is greater than 0, which is pretty much every time, you're never going to get R squared of exactly 1. The smaller that standard deviation, though, probably the stronger the relationship. So here's some of this key idea. The key ideas that we see here, right, are first that there's always going to be random variation away from our predictions. Our predictions are only correct on average, right? And variations from predictions are normally distributed with a constant standard deviation. Here you can see I took, this was kind of fun to do. I took that coordinate plane for our prediction, and I sort of made it three-dimensional, and I've put on top of it a bunch of little normal distributions, essentially showing that everywhere along that line, there is expected to be variation according to an identical normal distribution that's centered wherever the predicted value of Y is, but otherwise has the exact same standard deviation. Right now, if I go out about roughly 2 standard deviations from the mean, about 1.96 to be precise, how much of the area underneath those normal distributions am I talking about? 95%. So that key idea then is I sort of drew this rectangle, even though it doesn't look like a rectangle, it looks like a parallelogram because I drew in 3 dimensions. But that rectangle essentially describes 95% of our observations. We expect 95% of our observations to be within about 2 standard deviations of the predicted values. So if I just randomly generate values with these random variables, 95% of the time my points are going to sort of fall within that rectangle. That's kind of neat. Let's see this in another way. Here I have a new population equation. Y is a linear transformation of X, so that Y hat equals 30 plus 0.6X plus, some variation that's introduced by epsilon. So let's suppose that I let epsilon, our error term, have a standard deviation of just 0.1. 0.1 is pretty small. You could actually compare it to the slope of the least squares regression line. 0.1 is much smaller than the slope itself. And so, look at that. This is a random sample of 80 points from this population. Notice that its slope, 0.6012, is very, very close to the slope from our population. And there's an extremely strong relationship. 99.95% of the variation in Y's explained by the linear relationship with X. That standard deviation of the residual was so small, it allowed very little variation away from the line. What if I made the standard deviation of the residual slightly larger and I took about 80 observations? Now we see more variation. It's still a very strong relationship, but I can see by eye that it's weakened, that there's more variation above and below the line. R squared in this case was 96.3%. 96.3% of the variation in Y is explained by the linear relationship with X, less than previously, because there was more variation possible because of a larger standard deviation of my residuals. What if I made the standard deviation of the residuals even bigger, 5, which is way bigger than the slope of 0.6? What's going to happen now? Well, I would no longer call this a strong relationship. This would be a moderate relationship. Notice R squared is 0.375. The square root of 0.375 is like 3.875. That's like over 60, around 0.6 for a correlation, a little bit more than 0.6, which would make this a moderate relationship. And just to your eye, you can see there's a lot more variation away. Notice that there was more variability in the slope of the sample least squares regression line. The slope of the sample least squares regression line is still pretty close to 0.6, but it's 0.5458. There was a lot more variation, and therefore the sample slope wasn't quite the same as the true population slope that generated this particular model, right? So let's do some mathy problems to see how this works. Let's go back to our original least squares regression line, where we had 2 plus 3/4 X plus an epsilon. And epsilon was normally distributed with a mean of 0 and a standard deviation of 1. And if I plugged in x equals 4, I'm supposed to get 5. But what if I actually got 4? That's lower than predicted. What if I plugged in x equals 6? Well, according to the line, I should get 6.5. But what if I got 4, which is less than predicted? And what if I plugged in x equals 8? Well, then I should get y equals 8. But what if I got 4, which is, again, less than predicted? Which of these 3 observations was the least plausible? Which of these is most unexpected? Well, based on everything we said, it should be kind of obvious. But there's math that can prove it. Let's think about this almost like a p-value. Instead of just looking at these exact values, let's consider the probability of getting a point that is that far or even further below the least squares regression line, even further from our predictions. Let's go back to our 3D model with those normal distributions and calculate the probability of getting a y that's less than 4 for x equals 4, x equals 6, and x equals 8. Let's start with x equals 4. Remember, when x equals 4, we're expecting y hat to be 5, but what if I got y of 4? That would give me a residual of -1. So that would mean I can basically calculate a probability just using the distribution of residuals. What's the probability the residual will be less than -1? I could shade in my normal curve, and using technology, I can find out very quickly the area under that curve is about 1.1573. That's a 15.73% chance that I would get some residual less than -1. Well, what would be the residual for x equals 6? Once again, if y equals 4, well, that's even further below the prediction line. And so there I would have expected 6.5. That would mean 4 would give me a residual of -2.5. And the probability of getting a residual less than -2.5, you can see I shaded in there. That's a tinier area. It's only 0.0062, less than 1%, going from 15.7% to less than 1%, making it very unlikely. Well, you can see where this is going. If x equals 8, what's the probability of getting a y less than 4? Well, y hat equals 8 is our prediction. 4 is a residual of -4, and in this situation, what's the probability the residual will be less than -4? About 0.003. Did I have enough zeros there? 0.000032. Virtually impossible. Not actually impossible, but extremely unlikely to occur. So we can actually calculate the probability of observing particular events using normal distributions. Just thinking how far off a point would be from the prediction, turning into a residual, and using the normal distribution of residuals to calculate probabilities is pretty cool. So our big ideas, our key ideas, just to recap, remember that random variation due to other factors makes our predictions only correct on average when we're making predictions using least squares regression lines. And a fundamental assumption of least squares regression is that variations from our predictions are normally distributed with a constant standard deviation. The residuals that we observe will always have a constant standard deviation. Hope you learned something. Have a beautiful day, statisticians.